Hi, welcome to this recording for Unit 10. In Unit 10, we're going to be talking about the geometry of the moon, the earth, and the sun, basically the distances and sizes, and so on and so forth. Okay, we're going to take it from a historic perspective. So basically, show that the earth is round and its size can be found from basic observations. This was done by the Greeks. And explain how the ancients basically estimated the size and the distance to the moon and the sun, and discuss how the fact that Aristarchus basically suggested that the earth goes around the sun, that idea was rejected. Okay, and we believed then that the sun actually and everybody else also revolves around the earth, which is later on was corrected, and define the angular sizes and how we use geometry to find the distances or sizes of objects if we know one or the other. Okay, so Aristotle concluded from observations that the earth is round, and basically there are some key observations. Depending on your position on the earth, if you look at the horizon, and if you move either north or south, you will see that stars change location. Stars that did not, you can see them under a certain in a certain latitude. You will see them when you move one direction or the other, depending on which way you're moving. So his conclusion is that this proves, of course, that the earth is round, and you can see from the geometry basically what that means. Also, when you look at the shadow of the earth during a lunar eclipse, it's curved. It looks like it's circular. So if the earth is a flat circle, at least that's the first assumption, then it projects a circular projection on or arcs on the moon during a lunar eclipse, partial lunar eclipse. But then at any other time, it does that. So it can't be just a circle. It has to be a big circular shape that projects these arcs all the time, no matter what the lunar eclipse is. The other also notice that you can see also is that ships, when they move further and further in the sea and you're watching them from the shore, it's the bottom that starts to disappear, and then they disappear along that line. If you were to move closer to another shoreline and you observe the same ship, basically, of course, it's going to be coming, and then again, it's going to disappear at some later point, further than the first one when you were at the farther away the location. So again, that indicates that we're looking at a curved surface. So the earth must be curved, a spherical shape, whichever direction the ship goes. Okay, and it disappears from the bottom up, and then it starts to disappear. And when it comes to shore, also it comes from the top, and then it starts to appear from there. So it's basically coming from like a downhill, basically trying to rise to you. Okay, so that's basically the argument that the earth was spherical in shape. Aristarchus basically used simple geometry during a quarter moon. The assumption is that the sun is shining on the moon, and the moon is right in the perfect geometry where it's making a 90-degree angle. So this angle is a 90-degree angle. This angle is a 90-degree angle. If I can estimate this angle, okay, I can find, and this too, the sun is, you have to make an assumption, the sun is too far away that this, in this case, if I look at this right angle triangle, that the hypotenuse in this case and this side of the triangle are almost the same. So this angle will be very, very close from 90 degrees, just like this one, which is a 90-degree angle during the quarter moon. So you can estimate the size of the distance to the sun based on the distance to the moon. Okay, so basically that's the math. And he came up with some numbers, like 20 times the distance from the earth to the moon is the distance to the sun. And he came up with the size of the the sun being about 7 times bigger than the earth. Because of that, he had to conclude that it's not the sun that is going around the earth, but rather the earth going around the sun, because the sun is bigger. Obviously, his number is too far off in this case. We know it's about 100 times bigger actually than the earth. I'm sorry, the sun is bigger than the earth by about 100 times. So the reason is because this angle was estimated to be wrong. I mean, he didn't have a good measurement for it. So better measurement gives you much better answers and closer to the fact that this is about 100 times bigger. Again, as I said, Aristarchus, who is about 3 centuries before the current era, uh, estimated based on how many moons basically move move behind the shadow of the Earth during a lunar eclipse. Estimated the size of the moon to be about a third of the size of the Earth, and that's not far off. Actually, that's a good estimate. But and then he estimated also the time it takes, anywhere up to 5 hours basically for a lunar eclipse. Based on that, he used the geometry also to estimate the distance to be about 70 times the radius of the Earth. It's slightly off also because the actual distance is about 60 times. I mean, 384,000 divided by 384,000 kilometers divided by the radius of the Earth, which is 6,400. So the ratio is about 60, not 70. So it was a little bit off because, again, measurements sometimes they require a little bit more accuracy. So again, his argument that the sun is bigger than the Earth must then conclude that the Earth is the one going around the sun. Remember, this is 2 to 3 centuries before the current era. That's 2,200 years ago. He concluded, based on this difference in sizes, the masses, that the Earth must orbit the sun not the other way around. The small always orbit the big. But of course, his idea was rejected at that time because of the thing that is called the parallax. If we are here in July, for example, looking at this star in the sky, if it were true, they said, that the Earth goes around the sun, then 6 months later in January, that star, because of the parallax, you close one eye and you look at an object and you open your eye, that eye, and you close the other eye, and you will see the object shifts versus the background. Okay, you can do that at home. So you close one eye and you look at your finger, for example, and you open that eye and you close the other one, and you see your finger shifts versus the background. It's projecting this way, and now it's going to be projecting that way. So that's called the parallax, and that's a known geometrical fact. So, but now, instead of closing eyes, we are in January in one location on the sun. 6 months later, we're going to be in the opposite direction. So stars should shift in the sky. Obviously, we don't see the parallax, at least with the naked eye, because these distances are huge. So there is actually a parallax, especially for the nearby stars. But you needed equipment that is super, how should I say it, accurate enough to make that measurement. So right now with the eye, you can tell the star has shifted in location because it shifts with a fraction of an arc second, okay, in the sky. So again, so that's why the idea of the fact that the Earth goes around the sun was rejected. So we went back to the so-called geocentric model, where the Earth is actually the center of the solar system, including the sun revolving around the Earth. Okay. Eratosthenes, again, about a century and a half before the current era, not only he knew the Earth was actually circular, I mean spherical in shape, I should say, but he also was able to measure its radius. And that is because on a given day, which is June 21st, in southern Egypt, in the city called Cyan at that time, it's Aswan nowadays, you go there and the shadow of any stick, basically, there is no shadow. So if you look down, for example, on a deep well, the sun isn't immediately reflected in that location on that time. And in the same time, he knows that in the same day, that in the city of Alexandria, the shadow, you take a stick, for example, it's going to create a shadow that makes a 7-degree angle. So because he knew from Aristarchus' measurements at least, and other assumptions, that the sun is far away, so the rays that are coming from the sun must be parallel. So the ray that happened in Cyan is going straight to the Earth. The ray that is going to Alexandria on that same day is making a 7-degree angle. And using simple geometry, these two parallels are cut by the same line. So this also must be a 7-degree angle. So again, using geometry. So knowing the distance between Cyan and Alexandria, he paid people actually to walk that distance and measure the distance. And based on the arc distance and the angle, you can find the radius. There is a nice geometrical expression called, for the arc length is equal to r, radius times theta. Since you know theta, which is the angle, which is 7 degrees, you can find the circumference of the Earth. You can find the radius of the Earth. Actually, You can find the circumference quickly by taking the ratio of the entire circumference divided by the distance psi in Alexandria is the same ratio as 360 degrees going by 7 degrees. So 360 divided by 7 times the distance in here between those two cities, and that gives you the circumference. This was very accurate, actually. This measurement was very accurate. So we knew the radius of the Earth. If you work your problem backward, okay, since you know the radius of the Earth, you can find the distance to the Moon. Because remember, we said that Aristarchus estimated the distance to be 70 times. So you can say, oh, the Moon is about 300,000 kilometers away from, 400,000 kilometers away. Granted, this is a little bit off. It should be 60 only with modern measurements. Then you can find the size of the Moon because you just divide that by 3. Then you can go back and find the size of the Sun, although that's wrong, okay? And the distance to the Sun, although that's wrong. But at least you have an idea of the sizes. You see how the problem was worked backward? Initially it was pushed all the way to the size of the Earth. Now, since you know the size of the Earth, you can work your problem backward. Again, the angular size is a powerful technique because these distances are very far, these angles are very small. So you use, because this triangle, for example, and this triangle, they are similar triangles because they have to share the same angle in here, alpha. Therefore, the tangent of this angle alpha is the same thing as the ratio of the opposites over, in this case, the hypotenuse. The tangent is over the side, so the opposites over the side of the angle, which is going to be alpha over 2. But because these things are very, very small, these angles are very small, there is something called the small angle approximation in trig. And you use that to find the distance or the size. If you know the distance, you can find the size of the object. So, for example, if we know I can take a coin and put it close to my eyes, closes everything, and if I move it far enough to cover the size of the Moon or the size of the Sun, for example, I know that ratio of the size of my coin, quarter, for example, to the distance from my arm length to that is the same distance, the size of the Moon, for example, if I'm looking at the Moon, to the distance to the Moon. So that's basically how powerful this technique is. Again, using these ratios, this is what I'm talking about in here. You can keep alpha in degrees if you like. And you divide it by 360, 2 pi d is the circumference, and that gives you the actual size of the object. So this is how we use astronomy, use geometry, if you wish, to use it in astronomy to our size, to our advantage. Thank you.